Okay, I'd like to give an example of a more advanced mech. In this case, I'm going to create a recursive mech, which is a technique where a function calls itself. In this way, you can do a looping type of mechanism that's quite sophisticated and allows you to do some clever things. All right, so in this case, I want to create a function that will find the smallest factor of a number, which is the smallest integer that will evenly divide another integer. All right, so I'm going to call this function SF, and I'll have one variable n, which is the number that I'm looking for. Now, in this case, I'm going to need to send in my test number, which is the value that I want to see if it's a factor of it. So in this case, I want a helper mech, and I'm going to call this helper mech ISF for my internal smallest factor function. And again, I'll have that n parameter, but I'm also going to have a second parameter, which I'll call p, which is the number that I'm testing. And so my main function is just going to call down to the internal function. It's going to pass in the variable n, and it's going to start it out by looking for the number 2, looking to see if 2 is a factor, the smallest factor. All right. So the first thing I want to do is I want to check to see if p is actually a factor. If it is, then I'll know that I've found the smallest factor, and I'm going to return it. So the way that I do that is I'm going to take n divided by p. Now I'm going to know this is a factor if there are no decimal points in this result. So I'm going to use the floor function here on that bubble. And now I'm just going to check to see if these two are equal to one another. So I say, if this equals that. Now this is either going to give me a truth value of true or false, which is going to give me basically a 0 or a 1. And I'm just going to call this isFactor. Now, the way that you look for a smallest factor is that you start out with 2. Check to see if it's a factor, and then you just keep on incrementing upwards. Now, what I'm going to do is I'm going to continue. I have this if function that's basically going to tell me when I'm at the end. Let's take a look at the if function for a second. Let's go to the lexicon, and let's look at the if function. Now you can see that there are 2 forms of the if function. There's one form that takes all numbers in as parameters. If, then, and else parameters are all numbers, and it returns a number. And there's a second form that takes a number in for the if parameter, but takes functions in as the then and else parameters, and then returns a number. The way that Oovium works is that it will always evaluate the parameters of a function before it sends those parameters to the function itself. In a recursive function, by evaluating parameters first, you're guaranteed to always have an infinite loop. And so it's necessary to use this second form, where when it passes back a function, it doesn't actually evaluate the function all the way down, it just passes that function back, and then once the function gets passed back, then it does the evaluation. So rather than passing in actual number bubbles, I'm going to pass in a function bubble. And the way that I do this is I just take a normal expression and I embed it in brackets. Now, basically what I want to do is I just want to iterate our p variable by 1. So the first function I'm going to create is I'm just going to call down to ISF, this is the recursion. I'll pass in n, and in this case I'm going to pass in p plus 1. So I'm going to increment the p variable by 1. The other function is the case where I haven't found a smallest factor. There is no smallest factor. Basically, I found a prime number, and in that case, I just want to return the number itself. So I'm going to have a simple function that is just the number itself, just n. Alright, so I've got these two function data types, and you can see the bubbles are a different color. Now, if I were looking for the smallest factor, say the number 17, I wouldn't have to check all numbers from 1 to 17. As I'm checking for the smallest factor, I know that each factor has a partner factor, which is the two numbers that multiply together in order to get the number. And as I'm looking for smallest factor, I always know that the partner number is going to be larger or equal to the number that I'm looking for. So for 17, I look at 1, or 2, and say no, 3 is not a factor, 4 is not a factor. And when I get to 5, I can see that if 5 times something were equal to 17, that something would have to be larger than 5. But in this case, I know that 5 times 5 is 25, which is larger than 17. So there's no need to check 5. There's no way that 5 could be a factor of 17, assuming that no numbers prior to it had been factors. So what I'm going to do is I'm going to say if, and I'll say if p times p is greater than n, then I know I've found a prime number, so I will just return the number itself. Otherwise, I want to increment p. Alright. And I'm just going to call this my increment bubble. Alright, so then the last step is to put this all together. So I want to say, if I've found my factor, if it's a factor, then return p. P is the answer. I found it. Otherwise, I want to increment. Check the next p. And I'll call this bubble my result. And then I'll set the mech equal to the result. Alright, so here's my recursive mech that finds the smallest factor. So let's give it a try. I'm going to take the number 893. I can see in my custom area my functions now show up, so I'll call SF on 893, and gives me the number 19. And we can test this. We'll take 893 divided by 19, gives me 47.